Imagine a planet so far away that sunlight takes over 4 hours to reach it, a world usually shrouded in mystery and icy silence. That planet is Neptune, the outermost giant of our solar system. For decades, Neptune was known only through brief glimpses, like the fleeting visit of Voyager 2 in 1989, and the distant outlines captured by Earth-based telescopes. Its deep blue atmosphere, its faint rings and swirling storms were all that humanity could observe. But now, the James Webb Space Telescope has given us a front-row seat to an event of unimaginable scale. In real time, Webb detected something extraordinary, a massive object colliding with Neptune. This was no ordinary meteor streaking across the sky. The energy released by the impact was so immense it could rival millions of nuclear bombs exploding simultaneously. The shock waves from this collision continue to ripple through Neptune's atmosphere, leaving marks and distortions that have never been seen before on any planet in our solar system. This is a moment in history where science fiction meets reality. A giant object, possibly hundreds of kilometers wide, has smashed into a distant ice giant, reshaping its atmosphere and creating scars visible even from millions of miles away. Thanks to Webb, humanity is not just observing Neptune from afar. For the first time, we are witnessing one of the most violent and dramatic events in the modern solar system unfold before our eyes. When James Webb turned its powerful infrared gaze toward Neptune, astronomers expected to study the planet's usual features: its methane-rich atmosphere, faint icy rings, and turbulent storms. Instead, Webb captured something that defied all expectations. Sensors detected sudden bursts of intense heat erupting from Neptune's clouds, an energy surge far beyond what the planet's normal weather could produce. Neptune is one of the coldest planets in the solar system, with average temperatures plunging below -200 degrees Celsius. Its atmosphere, dominated by hydrogen, helium, and methane, traps very little heat from the sun. Yet, Webb recorded thermal signatures that suggested a massive injection of energy from an external source, as if a colossal object had violently collided with the planet, releasing unimaginable heat. In an instant, alongside the heat bursts, light variations rippled across the upper atmosphere, appearing and disappearing in a way that resembled Neptune being struck by an invisible cosmic force. These anomalies were not random. They were consistent, powerful, and unmistakably linked to a catastrophic event. Scientists watching the data realized that Neptune was undergoing something unprecedented, providing the first evidence that an extraordinary collision had occurred. For the first time, astronomers could see how a distant ice giant reacts to a sudden infusion of energy, with heat surging upward, disrupting clouds, and creating atmospheric turbulence on a massive scale. The planet's serene blue appearance was no longer static. It was alive with evidence of a violent encounter, all revealed through the sharp eyes of the James Webb Space Telescope. The moment the massive object struck Neptune, it sent shock waves rippling through the planet's thick, gaseous atmosphere. Imagine tossing a giant stone into a calm lake. The ripples spread outward in every direction. Now, replace that lake with Neptune, a planet 4 times the diameter of Earth, made almost entirely of swirling hydrogen, helium, and methane, and the stone with a colossal cosmic intruder. That is the scale of the disturbance captured by James Webb. These shock waves disrupted Neptune's jet streams, twisting and stretching clouds into patterns never before observed. Massive bands of clouds were deformed, some stretched thousands of kilometers across, creating what scientists describe as atmospheric scars. Storms that had been stable for years shifted, new vortices formed, and familiar dark spots on the planet's surface appeared to migrate or warp under the immense force of the impact. Unlike rocky planets, where collisions leave craters and scattered debris, Neptune's gaseous nature meant the impactor was swallowed by the atmosphere, its energy released across the entire planet. The result was a dramatic reshaping of Neptune's weather systems. Layers of turbulence, pockets of extreme heat, and swirling clouds painted a vivid picture of chaos on a planetary scale. For scientists, these ripples are more than just dramatic visuals. They are a real-time laboratory for understanding how ice giants respond to massive energy inputs. By observing the propagation of these shock waves, researchers can study wind acceleration, storm intensification, and atmospheric mixing on a scale impossible to recreate on Earth. Neptune, once a distant and mysterious giant, was now revealing its secrets through the scars left by a cosmic collision, captured in unprecedented detail by the James Webb Space Telescope. The sheer scale of the object that collided with Neptune is almost beyond comprehension. By carefully analyzing the thermal radiation and the shock waves captured by James Webb, scientists have estimated that the impactor was not a small asteroid or meteor. It was tens, possibly even hundreds of kilometers wide. To put this into perspective, the asteroid that is believed to have wiped out the dinosaurs on Earth 66 million years ago was about 10 kilometers across. The object that struck Neptune could have been 10 times larger, carrying energy on a scale almost impossible to imagine. Such an enormous body would have released energy that far exceeds anything humans have ever witnessed, even in our most powerful explosions. The collision sent tremors of heat and turbulence through the entire atmosphere, disturbing cloud systems, storms, and jet streams across the planet. Unlike impacts on rocky planets, where craters mark the surface, Neptune's gaseous layers absorb the object, creating a planet-wide reaction that continues to unfold even months after the initial strike. Scientists are fascinated not only by the size of the object, but also by what it tells us about our solar system. Large bodies of this scale are rare, and their presence in the outer reaches, such as the Kuiper Belt or as rogue comets wandering through space, reminds us that Neptune exists in a dynamic and sometimes violent environment. This collision provides a once-in-a-lifetime opportunity to observe how a massive ice giant responds to a cataclysmic impact, offering insights into the behavior of gas and ice giants both within and beyond our solar system. With James Webb providing real-time data, we can watch the aftermath of a cosmic event that reshaped Neptune on a scale far greater than anything previously imagined, giving humanity a front-row seat to the dramatic forces shaping the outer solar system. Where did such a massive object come from? Astronomers believe the culprit likely originated from the distant reaches of the solar system, either from the Kuiper Belt or as a rogue comet wandering through space. The Kuiper Belt is a vast region of icy debris and dwarf planets beyond Neptune, home to Pluto and countless frozen bodies left over from the formation of the solar system. Occasionally, gravitational nudges from Neptune itself or interactions with other objects can send one of these icy wanderers on a deadly inward trajectory. Another possibility is that the object was a rogue comet, a body that had been drifting through the outer solar system for millions of years. Once it crossed Neptune's gravitational influence, it would have been pulled inward, accelerating to incredible speeds before slamming into the planet's thick atmosphere. Neptune's gravity, 17 times stronger than Earth's, made escape virtually impossible, ensuring that this interloper collided with the planet with devastating force. Such events are extremely rare in the modern solar system. Collisions of this magnitude are thought to occur on timescales of millions of years, making James Webb's observation a stroke of cosmic luck. By studying the trajectory and energy of the impact, scientists can begin to reconstruct the history of these distant icy objects and better understand the dynamic environment of the outer solar system. This impact is not just a random accident. It is a vivid demonstration of the unseen, ongoing forces at work at the edge of our solar system. The violent journey of this object across millions of kilometers of space, culminating in a collision with Neptune, is a reminder that even distant icy worlds are part of a living, evolving cosmic system. The collision with Neptune left more than just atmospheric scars. It left a chemical signature that tells the story of both the planet and the impactor. James Webb's powerful infrared instruments detected unusual molecules in Neptune's upper atmosphere, including ammonia, carbon dioxide, exotic ices, and complex hydrocarbons. These compounds are not normally present in such quantities, making this discovery a clear fingerprint of the object that struck the planet. As the massive impactor plunged into Neptune's thick gaseous layers, it disintegrated, releasing its chemical composition and mixing with the planet's own atmosphere. The resulting chemical chaos created molecules that had never before been observed in Neptune's clouds, giving scientists a rare window into the makeup of both a distant Kuiper Belt object and the hidden layers of an ice giant. Some of the compounds may even have originated from the coldest regions of the solar system, carrying information about the conditions in the outermost reaches where sunlight is weak and temperatures approach absolute zero. This chemical footprint is more than just evidence of the collision. It is a treasure trove for scientists. By analyzing these molecules, researchers can trace the origin of the impactor, determine its history, and understand how it transformed upon entering Neptune's atmosphere. At the same time, the collision dredged up hidden materials from beneath Neptune's upper layers, revealing secrets about the planet's interior chemistry that were previously inaccessible. In essence, Neptune became a cosmic laboratory. Webb allowed humanity to observe a rare experiment in real time. A massive, pristine object from the outer solar system colliding with a distant ice giant, leaving chemical clues for scientists to unravel. Every molecule captured by Webb tells a story, from the icy origins of the impactor to the violent transformations that reshaped Neptune's skies. The impact of the massive object didn't just leave a chemical signature. It fundamentally reshaped Neptune's atmosphere. Normally, Neptune is a world defined by extremes. Winds howling over 2,500 miles per hour, storms larger than Earth, and dynamic cloud systems that shift constantly. But the collision injected an unprecedented surge of energy, supercharging these already violent systems and creating atmospheric phenomena never seen before. Jet streams were disrupted, clouds stretched into elongated bands, and familiar dark spots warped or even migrated in response to the force of the impact. Entire storm systems twisted, merged, or erupted anew, while massive vortices spun with speeds surpassing Neptune's normal maximum winds. This chain reaction of turbulence and energy release continues to ripple across the planet, leaving long-lasting scars in both motion and structure. The effects are not merely temporary. Scientists expect that some of these storms and disturbances may persist for years, gradually dispersing the energy from the collision, but leaving permanent changes in the planet's atmospheric circulation. The heat pulse from the impact continues to radiate outward, igniting chemical reactions in layers of methane and hydrogen, forming clouds and molecules never before observed. In essence, Neptune's atmosphere became a living laboratory. By observing how storms, winds, and dark spots respond to such an extreme event, scientists gain invaluable insight into the physics of ice giants. Webb's detailed infrared and visible light observations provide a front-row seat to this transformation, allowing humanity to witness in real time how one of the most mysterious planets in the solar system reacts to a massive, catastrophic collision. Neptune, once serene in its cold blue hues, now displays a dynamic, ever-changing environment shaped by violence and energy on an extraordinary scale. The collision on Neptune was not an isolated event affecting only the planet itself. The enormous energy released and debris ejected from the impact sent ripples throughout Neptune's entire system, profoundly affecting its moons and delicate ring network. Neptune's 14 moons, ranging from tiny irregularly shaped rocks to the massive and mysterious Triton, are bound by gravity in a finely tuned celestial dance. The sudden influx of energy and matter disrupted this equilibrium, offering scientists a rare glimpse into how planetary systems respond to cataclysmic events. Fragments of the Impactor, along with dust and ice particles, were flung far beyond Neptune's upper atmosphere, potentially interacting with the faint rings that encircle the planet. Unlike Saturn's bright, thick rings, Neptune's rings are thin, wispy, and difficult to detect. Even subtle alterations, such as temporary brightening, thickening of certain arcs, or the creation of transient streaks visible in infrared, provide critical evidence of the magnitude of the impact. These ring changes act like a cosmic signature, preserving a record of the energy and debris released during the collision. The moons themselves may have experienced direct effects from the event. Smaller moons, constantly bombarded by micrometeorites, could have acquired a new layer of material from the collision, subtly altering their surfaces. Triton, Neptune's largest and most intriguing moon, may have been especially affected. Its icy crust and thin nitrogen atmosphere could have reacted chemically with fallout from the impact, triggering temporary atmospheric or surface changes. These interactions may have produced new chemical compounds or modified the existing environment in ways that could persist for decades. Even the gravitational dynamics of the system may have been influenced. The sudden redistribution of mass and energy from the impact could introduce minor perturbations in the orbits of moons or induce shifts in the ring plane, creating ripples that slowly propagate through the system. Such changes, while subtle on a human timescale, could have lasting consequences for the architecture of Neptune's satellite system, demonstrating how a single catastrophic event can leave long-term marks on a planetary system. This event highlights an important principle in planetary science. No celestial body exists in isolation. A massive impact on a planet can cascade outward, affecting rings, moons, and even distant regions of the surrounding space. Observing these effects in real time allows scientists to study planetary system evolution with unprecedented detail. James Webb's sensitive instruments captured not just the immediate aftermath of the impact on Neptune, but also its subtle and ongoing influence on surrounding moons and rings. By monitoring changes in Neptune's rings and satellites, scientists gain insight into how energy, momentum, and material are redistributed across an entire system. The collision provides a unique natural experiment, revealing the intricate interplay between a massive ice giant, its moons, and its rings. This unprecedented observation allows researchers to better understand the dynamics of planetary systems, both within our own solar system and beyond, offering a template for interpreting similar events in distant exoplanetary systems. In essence, the Neptune collision turned the planet and its moons into a cosmic laboratory. The energy and debris from the impact continue to ripple outward, reshaping the system in subtle but measurable ways. With James Webb capturing these changes in exquisite detail, humanity now has a front-row seat to witness the interconnected consequences of a single, extraordinary event, a reminder that in the universe everything is connected, and even the most distant worlds are alive with motion, energy, and change. The massive collision on Neptune does more than illuminate the dynamics of our own solar system. It offers an unprecedented window into the behavior of distant exoplanets. Across the galaxy, astronomers have discovered thousands of planets orbiting other stars, many of which are classified as hot Neptunes or mini-Neptunes. These exoplanets often share similarities with Neptune in size and composition, but they exist under vastly different conditions, sometimes much closer to their host stars. Observations of sudden atmospheric anomalies or unexpected chemical changes on these worlds have long puzzled scientists. Now, the Neptune impact provides a real-world reference. By carefully studying the aftermath of this collision, including changes in wind patterns, storm formation, and chemical signatures, researchers can create models to interpret similar events on exoplanets. If a distant Neptune-like exoplanet suddenly brightens or exhibits new molecules in its atmosphere, scientists can compare these observations with the data captured by James Webb on Neptune to determine whether a recent impact might be responsible. This transforms speculative theories about exoplanetary collisions into evidence-based science. James Webb's ability to detect subtle shifts in temperature, chemical composition, and atmospheric turbulence on Neptune provides a template for understanding extreme events on planets hundreds or even thousands of light-years away. The same physical processes, energy redistribution, shock wave propagation, and chemical reactions triggered by high-energy impacts can now be studied and applied to distant planetary systems. This helps astronomers predict how rare, violent collisions affect atmospheric composition, storm intensity, and climate evolution on planets far beyond our solar system. Furthermore, Neptune's collision demonstrates the interconnected nature of planetary systems. Just as moons and rings were affected by the impact, exoplanets in multi-planet systems may experience cascading effects from similar collisions, influencing not only their atmospheres but also satellite orbits and ring dynamics. By understanding these processes locally on Neptune, scientists gain the ability to infer what might happen in distant, more complex systems where direct observation is far more challenging. The implications extend even further. By cataloging the chemical fingerprints and physical effects of impacts like Neptune's, astronomers can build a database of collisional signatures. Over time, this database will allow scientists to reconstruct the history of bombardment in exoplanetary systems, offering insights into how planets acquire or lose atmosphere, how moons form or evolve, and how planetary climates respond to catastrophic events. In essence, Neptune has become a cosmic laboratory, not just for understanding our own ice giants, but for unlocking the secrets of planets across the galaxy. Every storm, every chemical anomaly, and every atmospheric ripple observed by James Webb provides a crucial clue for interpreting the lives of exoplanets. Through this single extraordinary event, humanity gains a benchmark for detecting and analyzing high-energy collisions and sudden atmospheric transformations in distant worlds. This insight bridges the gap between solar system science and exoplanet research, allowing scientists to draw parallels between what we can observe up close and what we infer from light years away. The Neptune collision is not just a moment in our local neighborhood. It is a universal lesson, demonstrating that planetary evolution is ongoing, dynamic, and shaped by rare but transformative events throughout the cosmos. Thanks to James Webb, we can now witness these processes in real time, providing context for interpreting distant exoplanet phenomena and enhancing our understanding of planetary systems across the universe. By connecting local observations to faraway worlds, the Neptune impact ensures that humanity's knowledge of planets is no longer confined to static snapshots. We are now able to witness the evolution of planets, both near and far, as it unfolds. The James Webb Space Telescope, JWST, has long been celebrated for its ability to peer into the farthest reaches of the universe, capturing light from galaxies formed billions of years ago and revealing the earliest chapters of cosmic history. But the observation of Neptune's colossal collision highlights an equally remarkable facet of JWST's capabilities: its power as a real-time sentinel within our own solar system. While designed primarily as a deep space explorer, JWST has now proven it can monitor dynamic, high-energy events happening right in our cosmic backyard. By detecting the thermal bursts, shock waves, and chemical fingerprints of the impact on Neptune, JWST demonstrated a level of precision and sensitivity previously thought impossible. Its instruments can detect subtle changes in temperature and light, trace the propagation of energy across an entire planet, and identify exotic molecules introduced into the atmosphere. This dual functionality transforms JWST from a window into the distant past into a real-time observer of planetary evolution. It is both a time machine and a cosmic laboratory, capable of capturing events that may occur only once in decades, centuries, or even millennia. The implications for science are profound. Observing the Neptune impact allows scientists to study the physics of ice giants under extreme conditions. From wind acceleration to atmospheric chemistry and storm formation, JWST provides an unprecedented opportunity to understand how planets react to sudden injections of energy. This knowledge is not limited to Neptune. By establishing a benchmark for planetary responses to collisions, storms, and other transient phenomena, JWST offers critical insights into the behavior of similar gas and ice giants elsewhere in the galaxy. Moreover, JWST's observations bridge solar system science and exoplanet research. By monitoring Neptune in real time, scientists gain reference points to interpret sudden atmospheric anomalies on distant worlds. If an exoplanet shows a spike in thermal radiation, a shift in chemical composition, or the formation of unusual cloud structures, researchers can now compare these patterns to the detailed data from Neptune's collision. This capability turns previously theoretical models into evidence-based science, allowing astronomers to infer the causes and consequences of extreme events on planets orbiting other stars. Beyond its scientific utility, JWST's dual role emphasizes humanity's evolving relationship with space observation. For centuries, we relied on static snapshots, brief glimpses of planets, stars, and galaxies frozen in time. Today, JWST allows us to witness the universe in motion. It captures cosmic drama as it unfolds. The collision on Neptune, storms raging across distant planets, and the ongoing evolution of planetary systems. In doing so, it transforms our understanding of the cosmos from static to dynamic, from theoretical to observable. In essence, JWST's dual capability underscores a revolution in planetary science. It is not only a window to the deep past, but also a vigilant observer of the present. The telescope's versatility ensures that humanity can study both the origins of the universe and the evolving story of planets within our own solar system. From tracking high-energy impacts to monitoring subtle chemical changes, JWST has redefined what is possible in space exploration, expanding our understanding of planetary evolution on both local and cosmic scales. Through the Neptune collision, we witness the telescope's transformative power firsthand. It has given humanity a front-row seat to observe the universe's most dramatic moments, turning science fiction into science fact. JWST proves that even in the vast, distant reaches of our solar system, we can now watch cosmic events unfold in real time, capturing the living, evolving story of planets, moons, and entire systems across space and time. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.